All right, physics students, today we're going to talk about curved mirrors, and we've got two different types. And the first type is the concave spherical mirror, and this is one where the reflecting surface is a segment of the inside of a sphere. You can sort of see something like this when you look at your reflection in a spoon. A spoon is actually more of a parabola shape, but imagine this picture right here is just a slice off a larger sphere, and you can look inside that. Now, the nice thing or the cool thing about a concave mirror is that it can form both real and virtual images. So what is a real image? A real image is an image that I can actually project onto a screen. A virtual image is something that really only exists in Mirrorland. You can see it. It's like looking at a flat mirror when you look at yourself, but that image cannot be projected. But here with a concave mirror, we can actually have a real image. If I put a sheet of paper right here and I had an object right here, there would be this image forming on that sheet of paper or on the screen. Now, concave mirrors have what we call a focal point. It's the place where if you had all of the lines of rays of light coming in from infinity, they would all bounce down through the focus. Now, this equation right here is the mirror equation, but it's also the thin lens equation. And I've talked about these letters earlier. P is your object distance, so it's how far the actual physical object is from the mirror. Q is the image distance. This is how far away your image is from the mirror. And then F is the focal point. We didn't really talk about a focal point with a flat mirror because flat mirrors' focal points are at infinity. All right, now, when we talk about mirrors, we talk about the front side and we talk about the back side. The front side is the real world where we all live, where you have actual physical objects. The back side is that mirror land that I talk about. Again, you can walk to the other side of a mirror and you're not going to see anything there. But when you look into a mirror and you see those virtual images, that is where the virtual back side is. P and Q are positive when they're on the front side of the mirror. So out here in the real world, Q is negative when it's on the back side. Now, images can be changed in size. So we say that they're magnified. And this is our equation for magnification, negative Q over P. This is H prime. This is the height of the image that forms. H is the actual height of the image. So if something has an image that's 3 times the size of its regular actual height, then we would say it was magnified 3 times. If it's half the size, then we would say that it has a magnification of 0.5. If the magnification is negative, it means that our image has turned upside down and is real. All real images are inverted. Now, I'm going to have you you can probably just pause the video here and write down these steps for doing ray diagrams. I'm also going to post a video that shows me doing several examples of making ray diagrams for concave spherical mirrors. All right, so now I'm just going to run through some possibilities and we'll do an activity where you kind of practice with this. And you don't have to have this memorized, but you do need to kind of know how it all works together. So first of all, this is a concave mirror, and you can see here is the focal point. Now, there's this thing called the center of curvature, and the center of curvature is a distance from the mirror that's twice the distance of the focal point. And imagine this mirror made a big circle. That would be the center of the circle. Now, it's an important position here because when you have an object that's actually at the center of curvature, that is also where your image is going to form. Now, if my object starts out way out beyond the center of curvature, any image I form is going to form in between the center of curvature and the focal point, and it's going to be smaller and it's going to be inverted. And I'm just going to kind of show you what happens as you get closer and closer. So now I bring that object into the center of curvature, and as I said, the image will form at exactly that place. Now I bring the object in between C and F, and now my image actually moves away. So you can see that as the object approaches the mirror, the image moves away and it gets larger and larger. Now, once I get that object to the focal point, all of the rays of light come off parallel. They're never going to converge, and they therefore never will make a real image. In fact, there won't even be a virtual image theoretically. So parallel lines, no images at F. And then when I bring that object inside the focal point, no image will form. Here's a reflected ray. Here's a reflected ray. You can see those rays are just going to get farther and farther apart. We extend those reflected rays backward to form our image virtually. And that is an upright magnified image for a concave spherical mirror. Their virtual images are always larger and upright. So this is just kind of a spreadsheet showing everything I just talked about. Again, I think the best thing to do is not necessarily memorize this, but really memorize or just kind of understand the process of how things change as you approach the mirror and as you cross those threshold lines of C and F. All right, so then that brings us to what if we have a mirror that's bent the other way? So it's kind of bending toward us, it's bulging toward us. And that would be called a convex mirror. And we see these all over the place. We see these in the corners of convenience stores or in libraries, or this looks like a museum maybe. Your rear view mirrors are convex mirrors. This is a tanker truck, and that is a convex mirror. And so what is it exactly that convex mirrors do? Well, convex mirrors always produce virtual images, and those virtual images in a convex mirror are always smaller. So this is like looking at the backside of a spoon. If you look at your reflection there, you'll see a little tiny image of your own face. The focal point of a convex mirror is on the back side. So mathematically, it will be negative. And then C is on the back side of the mirror as well. Now, spherical mirrors, like I said, a real slice out of a sphere, work pretty well when their diameter isn't huge. But as they get bigger and bigger, we start seeing an increase in what we call spherical aberration. And I talked about how there is a focal point of a mirror. Well, in reality, different spots along the curvature of the mirror will actually focus at different points that aren't that far away. But if all these lines aren't coming together into one point, you're not going to have a very clear image. You're going to have kind of a fuzzy image. And that's called spherical aberration. And so we can correct that by actually shaping mirrors to be more parabolic. That way they all will focus their rays onto that focal point. And it's just a product of the geometry of what we're doing here. So you reduce the number of focal points, you get sharper images with very, very slight parabolic shapes. The Hubble telescope that's given us tons of great images did not originally give us great images because they did not have the exact shape they needed. And they were off by literally fractions of a millimeter. But it made a big difference when you're looking across the galaxy.